Let's look at the section on the chain rule. So if you remember in algebra class, you learned about composite functions. They were a function of a function. Like I always think about your paycheck as a function of how many hours you work, and then maybe you put it in a savings account and actually get interest. So your function could be based on the number of hours you worked and then based on your interest rate. But a lot of times you'll see this, I always laugh because students call it fog, but this f of g of x. And usually this last piece here is how you see it written. So if I had two functions here and I wanted to compose them, what I do is I start with the inside. And so where I see g of x, I plug in x squared. And so now instead of f of g of x, I have f of x squared. And I plug in x squared where I see an x into my 2x plus 3. And I get my composition function. So that's just a little reminder if you don't remember too much about composing functions. They're just a function within a function. Again, which this function might be your paycheck. This function could be the interest rate of your savings account. So let's look at how we take derivatives of composition functions, and that's what's known as the chain rule. So the chain rule basically says that if I have u equals g of x, and this is composed of two functions, this f of u and g of x, so what I can see here is u is actually a function of x, and that's where I get my composite function. And you'll start to recognize these, how do you know if it's a composite function? To actually know to use the chain rule, and I'll give you some hints on those of how you recognize them. So to take the derivative then, what you're doing is you're taking the derivative of this entire function by taking the derivative of, I like to call it the outside function times the derivative of the inside function. So down here, if you kind of like the primes better, if I have y equals f of g of x, notice I take the derivative of the outside, the f of g of x, times the derivative of the inside, g of x. Now there's multiple ways of doing this, and I will tell you, if you learn to use this substitution method that I'm going to show you, it makes it a lot easier. I mean, it's not easy because it's a lot of steps, but it'll help when we do some things a little later. So basically what I do is I figure out what's the inside function. So nicely, an inside function would be like inside parentheses. An inside function might be a denominator, might be an exponent, might be what's under a square root. So I define that first. I define my inside function, and I call that u. You can call it any variable you want, but I just call my inside function u. So if this is the inside and I replace this inside with u, then my outside becomes y equals u squared. So this is the big key, that you can separate this. I can see this is composed of two functions. It's composed of a u squared, and then when u is 2x squared plus 1. Once you figure this out, then you just take the derivatives. Take the derivative of y, so bring the 2 down, 2u. Take the derivative of u, 2 times 2 is 4, and I subtracted 1. So this is using my shortcut rule. So I found the two pieces here. I took the derivative of each. I then multiply the two derivatives together, 2u times 4x. And then last, I substitute back what u was. So I had u equals 2x squared plus 1. So where I see a u, I substitute this back in. And I went ahead and multiplied 4x times 2. And I can even do another step. I could actually multiply, distribute the 8x, and get my final answer. All right, so just to recap, you're looking at an outside function and an inside function. Once you get those labeled, you take their derivatives, you multiply them, and then you substitute back. Okay, so we just saw how to do this whole substitution thing. This is a way that I use. I kind of call it a shortcut, and I'm not saying it's a good way. Some students like it, some like that last way because it's kind of more, step by step, get your u, get your y, take derivatives. What I do is I look and I see overall, I could take the derivative using the power rule by bringing that 2 down, leaving the inside alone, and subtracting 1. That's the first step. So this is the derivative of the outside, and I leave the inside alone. Then I take the derivative of the inside, which would be 4x, because 2 times 2 is 4. I subtract 1, and of course the derivative of 1 is 0. And now I simply multiply these two together, and then I distribute. So you can see, wow, that's kind of cool. That's a lot less steps. However, it's kind of nice when you get into more complicated ones of these to line them out with your y equals u squared, u equals 2x squared plus 1, because you're going to see that will actually help later. Now, some of you may have noticed, well, why not just multiply, just FOIL this out? 2x squared plus 1 squared means just to FOIL this out. So I multiply 2x squared times 2x squared. I get 4x to the 4th, 2x squared times 1, 2x squared times 1. I add those as how I get 4x squared. 1 times 1 is 1. And now I just use the power rule. I do 4 times 4, subtract 1 from my exponent. 2 times that 4, my constant's going to be 0. Multiply 4 times 4, and I get 4 times 2 is 8. Okay, so in other words, this is just another way you could just multiply these out. And some of you are sitting there going, man, that's way easier. Why would she show us all that other junk? Well, do you want to do this? What if it was to the 100th power? I don't know about you, but I don't want to do 100 of these. And that's why you learn this chain rule when it gets more complicated, that you can't just FOIL this out. But if you can, like squared, go on with your bad self and do it, right? Makes it easier, as you can see. So let's do a couple of examples here where you're actually writing them out, right? You're not just sitting here staring at the screen. You got your pencil and paper, and you are going to work these with me, correct? That's what I thought. All right, so what I do is I kind of go over here to the side, and I can see that my y would equal u to the 4th, because that's my outside function. And then u would equal 3x plus 1. That's my inside function. I take the derivative of each of these, so I bring the 4 down, subtract 1 from the exponent. The derivative of this one, let's put a line in between there, of 3x is just 3. So my derivative of f of x would be 4u cubed times 3, which of course would be 12u cubed. And then your last step, just don't forget to substitute that back in. So I would get 12 3x plus 1 to the 3rd power. Okay, so this is using this whole substitution. Again, this is probably the better technique to learn this way. And this is my final answer for my derivative. Let's look at another example. So get your pencils ready. So this would be the same thing. I would let my y equal u to the 7th, and u equals x cubed plus 4. Now, the only problem here is there's already a y being used, so if you wanted to, it doesn't matter. This is just a variable. You could call that z. The only reason why that might be confusing, because I'm going to have a y prime over here, and I don't want another one over here. Okay, so I'm doing my derivatives, so that's 7u to the 6, 3x squared. Now my y prime is going to be 7u to the 6 times 3x squared. I can multiply that. 21x squared. U is x cubed plus 4 to the 6. So all I did was I went ahead and just substituted in during that step. Oh boy, this looks like a quotient, or is it? What if I rewrote this? So what if I'm really taking the derivative of t squared plus t plus 4 to the negative 3? Remember, I can carry all this up here since it's all in parentheses and put that to the negative third power because I don't want to use the stinking quotient rule. Well, so then over here, I'm going to have y equals u to the negative 3, and then u equals the inside plus 4. So again, this is my inside. That's what I'm calling u. And now I can take derivatives. I bring the negative 3 down. I'm subtracting 1. So negative 3 minus 1 would be to the negative 4, and then my u prime would be 2t, and what's the derivative of t? Just 1, right? Because that's 1t. So I come over here, and my derivative would be negative 3u to the negative 4 times 2t plus 1. I could make this look a little better, meaning I could, well, let's just go ahead and plug in my u, which is t squared plus t plus 4 and 2t plus 1, and don't let me forget my negative 4. You almost let me forget that, right? Right there. So that's all I've done was where I saw a u, I plugged back in my u. And I could bring this back down to the bottom, or why bother? That would be my final answer. The reason I say why bother is because most of the time you're just going to plug in numbers when it comes to a word problem for these anyway. All right, let's keep going with these examples. Ooh, look at this bad boy. Remember I said the inside is typically within a parentheses or under a square root, an exponent. So I could rewrite this as 3 minus w to the 1/2 power, right? You remember that the square root is the same as the 1/2 power. So then my y would equal u to the 1/2, and my u would equal 3 minus w, because my u is the inside. So y prime would equal 1/2 u. Now remember here, let me just do this if you don't have this one down yet. I'm subtracting 1. So to subtract 1, I need to make that a fraction, 2 over 2. 1/2 u to the negative 1/2. 1/2 minus 2 over 2. And I could bring that 1/2 to the bottom and make it positive. And finally, my last step, and I always say students usually get where they have this memorized, that they can go from this step all the way to that step, because you see these square roots a lot. So in other words, the derivative of the square root of u is 1 over 2 square roots of u. U prime, the 3 goes away. That would be a negative 1, because there's a 1 right there. And so all I have over here then is my h prime of w, 1 over 2 square roots of u times negative 1, which equals negative 1 over 2. And let's go ahead and plug in my u. So not so bad. But, you know, a lot of steps for this square root if you don't have this piece memorized, and you'll get it memorized after a while. All right, let's see. Let's just keep on going. Whew, look at this one. Okay, this one looks like it could be complicated because it looks like I probably, if I could bring this to the top and use the product rule, but I'm going to go ahead and just use my quotient rule. So my quotient rule says I leave the bottom alone times the derivative of the top minus leave the top alone times the derivative of the bottom all over the bottom squared. Okay, so that's my quotient rule. So what I could do here is just kind of on the side, when I take this derivative, I see this is my chain rule where y equals u to the fourth, u equals x cubed minus 7. So y prime equals 4u to the third. U prime equals 3x squared. You got them power rules down, right? I brought the 4 down, subtracted 1, brought the 3 down, subtracted 1. You got to get those power rules down pretty quickly so you can start to do these very quickly. So now all I'm going to do, and then of course I could go ahead and write this one over here, which is going to be what, 6x squared, because 3 times 2 is 6. And then I subtract 1. Let's go back to my lovely purple. So this is going to equal 2x cubed times 4u, which is x cubed minus 7 to the third power, times 3x squared. So that's just these two pieces multiplied by that, minus x cubed minus 7 to the fourth times this derivative, 6x squared, and then all over 2x cubed squared. Now, in a typical mathy class, not a business math class, I would say you should multiply all this stuff out and make it look better. You don't need to do that in this class. What I'm looking for is that to make sure you can use, again, this is the quotient rule, and see that you can find derivatives. And the reason why is because typically what you're going to do is this is going to be a word problem anyway, and you're going to end up plugging in numbers for x. So who cares if you want to sit there and make this look better? You can, but you don't have to. Okay, let's see what's going on here with this application. So it says the total cost in hundreds of dollars of producing X calculators per day is given by this equation. And here's our domain. So we're producing X calculators, so between 0 and 50 calculators. Find C prime of X, which means find this derivative, and interpret C prime of 4. All right, so C prime of X then would be the derivative of 11, which is a constant, so that'd be 0, plus the derivative of this piece, which is going to be a chain rule. So I'm going to have y equals u to the 1/2, right? That's the same thing as the square root of u. And then u equals 2x plus 56. I already said you should get this one memorized, so you don't have to go through all those steps. U prime is 2. So I'm going to end up here with 1 over 2 square roots of u times 2. And of course you can see that cancels, so I'm going to get 1 over the square root. Let's go ahead and plug in what u equals. And so this would be my actual derivative. Okay, so once I take the derivative, then I'm ready to evaluate it at 4. And so I plug in square root of 2 times 4 plus 56, which equals the square root of 8 plus 56, which equals 1 over the square root of 64. Square root of 64, 8. Now, this is kind of where I kind of like that whole dy dx stuff, okay? And in this case, it's dc dx, which means this is the change in cost in hundreds of dollars. And I could take this, I said hint, multiply your result by 100 to get this in dollars. So if I multiply this by 100, I get 12.5. And basically, this again being a derivative is the rate. Okay, so my cost is changing $1 per 8 calculators, or at a rate of this $12.50 per, we could put a 1 under it, right, per 1 calculator. Let's look at another application. The number of X of bicycle helmets a retail chain is willing to sell per week at a price of P dollars is given by this equation, where our willing to sell per week, our price is between 20 and 100. I want to find this derivative, so the change in the number of bicycle helmets with respect to the price. So I changed the square root to the 1/2 power. This, you're going to see I kind of shortcutted it, so let me kind of show a couple of more steps here. So what I did is I brought the 1/2, so 80 times 1/2 is where I get the 40, and then I subtracted 1, which is where that came from, and then I took the derivative of the inside, the P, which was 1. Okay, so in other words, what I did is I said, well, y equals u to the 1/2, u equals p plus 25, u prime is 1, and my y prime is that 1 over 2 square roots of u, which is the same thing as this piece right here to the negative 1/2 power, because I took that 2 and divided by 80. So just to make sure you understand how I got that. So I have my derivative. Says find the supply and the instantaneous rate of change. That's my derivative of supply with respect to price when the price is $75. Well, so what I'm going to do is I'm going to plug in 75, okay, for my supply. This is X is my supply. So I get my supply, 400 bicycle helmets. And then I plug into my derivative, the price 75, and I get this rate, which is 4. And this says at a price of $75, the supply is 400 bicycle helmets per week, and supply is increasing at the rate of 4 bicycle helmets per $1.